Based on this, let me give you a couple of examples of how you might see something like this. And you might want to write these down and always have these handy so that you can refer to these standard, I should say common 7 functions that you will often have to do transforms on. So based on that, a couple of examples how this might work is, let's just give you some creative examples here. So if I have Laplace of, let's say the number 3 here, notice that can be written as Laplace of 3 times 1, which means I can pull this 3 out, and I'll get to some properties later on. Pull the 3 out because it's a constant, and I wind up getting 3 times the Laplace of 1. And what I wind up having is this 3 multiplied by this Laplace of 1. Well, Laplace of 1 is 1 over s. So this winds up being 3 over s. So then the Laplace of, say, 3, or any constant for that matter, but in this case 3, would just be 3 over s. You can do the same thing here. Say we're dealing with a function f of t equals, let's say, t to the 3rd. Then the Laplace of f of t would be equal to the Laplace of t cubed, because that's what f of t is, and that's going to be equal to, just follow this, where n is that n. So this would be a 3, that's a 3, so we got 3 factorial over, and that would be a 3, so 3 plus 1 is 4, so this would be over s to the 4th, so this winds up being 3 times 2 times 1, 6 over s to the 4th. And there's your transform. And similarly, you can go on and do some other examples. I'll just do a couple more here. Let's suppose f of t is equal to e to the, let's say, 5t. Recognizing that this function is the same form of this right here, then I can say the Laplace of e to the 5t will be equal to 1 over s minus this a represents that a, so we get a minus 5. And there's your Laplace transform for this. All these have been done in the same manner that we proved this one, and I think it was this one right here where n was 1. I can jump down even to one of these and say, what if we have cosine of, let's say, 5t over here? What would the Laplace transform of cosine 5t be? And it's a matter of just plugging stuff into whatever the k that corresponds, this k corresponds to that k. So we wind up getting s over s squared plus, we can call this 25, since that is 5 squared. Okay, so there's some basic examples of how to use this list of 7 common functions of which we'd want to take the Laplace transforms of. So hopefully that gives you a little bit more detail as to what's going on with these transforms. And let me re-emphasize that this is all based on, or I should say, these are only applying on functions right now with one input variable, and the procedure is the same for 2 input variables, but we'll get to that into more detail later. Going back to what we started, we had this ordinary differential equation where we're looking for some function y of t. So I'm going to show you how this works, how you would actually apply a Laplace transform on an equation. We're looking for some solution y of t. What you do here is you take the Laplace transform of the entire thing, so that turns into taking the Laplace transform of left side and right side. So you're going to get Laplace of dy dt plus 3y. I'm taking the Laplace of the entire left side, and that's going to be equal to, well, whatever you do to the left, you must do to the right. So the Laplace of 13 sine of 2t. Notice all I've done here is I've taken the Laplace of both sides. Once again, this is just another approach for solving this differential equation using transforms. What this simplifies to is this Laplace transform. If you notice, I've actually put some properties here of the Laplace is a linear transform. All that means is if I'm taking functions that I'm adding together, which is kind of what I have here, dy dt and 3y, I can break those up into 2 different transforms. What that means is this right here breaks into 2 transforms of Laplace of dy dt plus the Laplace of 3y, and that's equal to, of course, the right side, which is the Laplace of 13 sine of 2t. And also, another property of this is that if we have a constant, kind of this alpha here, and with a function ft, that constant can be pulled out in front of the outside of the Laplace, I should say. So notice what we've done here. We've taken two functions that are being added. The Laplace is acting on both of those. Going from here to here, we've broken up into two different Laplace functions, and we've taken out the coefficients, I should say the constants. So this winds up changing into the Laplace of dy dt plus 3 Laplace of y equals, I can do 13 times the Laplace of sine of 2t. And that's just a way of simplifying it. So what that winds up being now is I have three different Laplace transforms that I have to worry about. You have the Laplace of a derivative, which we haven't discussed yet, but we do know what these Laplace transforms of the y function and the sine of 2t. We can look back at our chart, and I went ahead and wrote those two specific ones down here just so that I can show you how that works. What this will wind up reducing to, or simplifying to, is the Laplace of dy dt, not equals, but plus, I should say plus 3 times the Laplace of y. And if you remember the Laplace of y, this is a y to the first power here. Once again, we're looking for y as a function of t. Y to the first power means that I would get n is 1. Oh, let me back up 1 second. Hang on. Okay, I should probably reemphasize what's going on here. We got, so I said the Laplace of y to the first power. Remember that this right here is a y of t function. This can be written as a big Y of s, because I know that this is going to wind up transforming this y of t function into some big Y function of s. So I can rewrite this as 3 big Y is equal to 13 the Laplace of sine 2t. I can go back and actually you look at this and say, well, the Laplace of sine 2t, where 2 is the k, I can reuse this formula here and just plug that into here. So this winds up being 2 over s squared plus 4. So the question now is, I have this big Y function, which is going to, ultimately what I'm trying to solve for in this whole thing is this big Y function. So I'm looking for this y of s. Now you might be thinking, well, how is this different than this? Well, what happens here is that this is going to turn into an algebra problem. Now I haven't quite shown you that because I haven't shown you how this transforms. But in the next video, which is going to cover Laplace transforms of derivatives, it'll cover what's going on with this transformation of this derivative. And I'll revisit the same problem. But ultimately, for now, I just wanted you to realize how to actually, what happens when you have an equation, take the transform of that equation, how it breaks into its different transforms, and then how, especially this term right here, you go and you inspect, by inspection I should say, you compare this to the common formulas that you have, and this go and replace what the transform is and multiply it by its constant. So we still have some unfinished business, which I'll actually cover in the next video, which will be Laplace transforms of derivatives. Until now, just concentrate on how to do the transforms directly from a function of one input variable, and hopefully you'll be able to get that pretty easily, and I'll give you some practice problems to do on the next lesson.